Okay, so be looking here at chemical reactions, except for in 4.7 pretty much covers precipitation, acid base, and redox, so I broke them up separately into their strands. So we're going to be covering the 4.7 parts of redox and the 4.9. Technically, redox is oxidation reduction reactions, but to me that's like writing it backwards, but it is redox. So what are we going to be doing with redox? Identifying redox reactions, assigning oxidation numbers to atoms in the reactants and products, determine if an element or atom is oxidized or reduced, represent balanced redox reactions using half reactions, and balanced equations constructed from half reactions. Now, this is your regular synthesis type reaction here. We have 2 sodiums plus the 1 chlorine, Cl2, and then we get our NaCl over here. Normally, we would be thinking of this as just a regular synthesis reaction. You're taking 2 elements, putting it together, getting an ionic compound. And that's kind of the Chem 1 perspective. This is supposed to have 2 over here too, to make it balanced. But Chem 1 perspective, this would be synthesis. But now, we're not really going to be looking at this in terms of synthesis anymore. This is going to be classified under the redox, and we'll show you why. Same thing here with this regular kind of combustion reaction. We have hydrogen reacting with oxygen. Oxygen being the reactant there means it falls under combustion to produce H2O here, water vapor. This is also no longer going to be just thought of as combustion here, or this would also could be synthesis because you're adding 2 elements together. This is going to fall under the redox umbrella. Because redox is a transfer of electrons. And it may occur to form ions, because that's transferring electrons may give you charged particles. Oxidation is when there is an increase in oxidation state. So increase in oxidation state means your number is becoming larger or more positive. In order to do that, you must lose electrons, because electrons by definition are negatively charged particles. So if you lose negatively charged particles, you become more positive. Reduction is a decrease in oxidation state, which is a gain of electrons. You're gaining those negative particles, so your oxidation number is going to decrease or become more negative. Oxidation state in general is just a number assigned to the element to keep track of where the electrons are and the electron count at that point. So basically, they look similar to formal charges, but really it is just a record keeping system to keep track of electrons. An oxidizing agent is the reactant that causes oxidation. So in order to cause oxidation, have to be willing to take electrons, because you're causing the oxidation of the other element. The other element has to lose electrons. So an oxidizing agent is really the reactant that contains the element being reduced, and the reducing agent is the reactant that causes reduction. So it's going to contain the element that is being oxidized. So these two are kind of opposite, and we'll go through them. They're not going to be tested on the AP exam, but we will just talk about them briefly because, like I said, within the textbook and other things, there are certain things I can't omit, or then you won't be able to work all of the problems. But the oxidizing and reducing agents are really just opposite of the elements being oxidized and reduced. So now if we're looking at this particular reaction as a redox, what you would notice here is you would assign oxidation numbers to the chemical species in the reaction, and you would see who's gaining and who's losing in their oxidation state. Does anybody remember from last year what number you assigned to things in their elemental form?
0.
They do get a 0. So hydrogen is 0, oxygen is 0 here. Because they're both in their elemental forms, even though they're diatomic, they're still in their elemental forms. Now in the compound, water here, water vapor, oxygen carries a -2, the hydrogen carries a +1 based off of assigning oxidation number rules. We'll go over those in just a minute. But as you can see, the hydrogen goes from 0 to +1. It's going from 0 to +1. So is that being oxidized or reduced?
Reduced.
Is it increasing its oxidation state or decreasing its oxidation state? It's increasing its oxidation state. Went from 0 to +1. So this one's being oxidized.
It gained electrons.
The oxygen goes from 0 to -2. You see a decrease in the oxidation state down by 2. Goes down by 2. So in this case, the oxygen is being reduced. Now we're looking at the sodium example and chlorine example. We have Na, we have Cl2, NaCl. Sodium in its elemental form gets a 0. Chlorine in its elemental form gets a 0. This is ionic compound. It follows its normal formal charge. So chloride's -1, sodium's +1. This case, the sodium 0 to +1 is going to be oxidized because it's increasing its oxidation state. Chlorine going from 0 to -1 is being reduced. Now, a good way to remember, I always have used oil rig. A couple years ago, though, about 5 years ago, somebody pointed out the Leo Gur. Leo the lion says Gur, I guess. So oxidation is loss. We're talking about electrons here. Reduction is gain. Or loss of electrons is oxidation. Gain of electrons is reduction. So you can use either system to remember which way it's going. So here comes the rules. Oxidation state of an atom in an element is 0. Yes, this includes the diatomics. So the 7 diatomics get assigned 0s as well. Oxidation state of monatomic elements are the charge that they are given on the periodic table. Like, for instance, if it tells you it's iron 3, has the Roman numeral 3 next to it, that means the charge is going to be +3, or the oxidation state would be +3. Barium being in group 2, alkaline earth metals, that whole column only does +2, so its oxidation state would be +2. Now, oxygen is usually -1. There's a couple exceptions to this rule though. Except for in peroxides where it's -1. Peroxides are written like this. O to -2, so that means that each oxygen carries a -1. And there aren't many peroxide compounds out there, but like one that we will be using in the lab is hydrogen peroxide, and it's written H2O2. There are a couple others like potassium peroxide. There aren't many peroxide compounds out there, but it will tell you in there that it's peroxide, so you know that the oxygen's carrying the -1 rather than a -2. The other case where it may not be assigned a -2 is if it's in a compound with fluorine. Fluorine is the most electronegative element on the table. So if you have to decide between oxygen and fluorine who gets to be assigned the negative number, it's going to be fluorine because it's more electronegative. Remember, electronegative means that it's going to be attracting electrons to it. Hydrogen is pretty much going to be +1. There's a rare occasion when it's in a hydride, which we don't really use anyways, but what does a hydride look like? A hydride would be like NaH. That would be sodium hydride. In that case, sodium gets the +1 and the hydrogen would take on the -1. Sum of the oxidation states is 0 for neutral compounds. And the sum of the oxidation states for polyatomic ions are going to be the charge that is on the polyatomic ion. Now for the nonmetals. Nonmetals follow this priority chart here. Okay? Nonmetals higher on the table take priority, and that's based off of electronegativity, really. Fluorine is the most electronegative, so it's going to be assigned the negative first. Oxygen's then the next most electronegative element, so then it gets assigned the negative. Halogens are more electronegative than the oxygen group, and the oxygen group is more electronegative than the nitrogen group, and so forth. Okay? So you would follow this priority, and like I said, they had this one on an AP exam, and that's why I'm highlighting it, this example. If you have OF2, which is a compound, a covalent compound, the F gets assigned the -1 because it's more electronegative. The O gets assigned the positive in this case, which seems kind of odd, but yes, in this particular case, F is -1, the O would be a +2. And that seems weird, but this is a kind of one of those anomaly exceptions. But it has shown up before on AP questions. Now, a couple other things. We write oxidation numbers above the element in question in the chemical equation. They always show the charge, so don't just put 2. If it's +2, it needs to have a plus sign and then the 2. So show the charge. If it's the -1, put negative and then the number. They are always written for one element. The charge is always written first, followed by the value. So it's opposite of formal charge. So if I was writing an ion, say I was writing N3-, this is nitride. All right, like that. But if I was writing it in this compound like so, this potassium nitride compound, you would write -3 on top like that. Okay? So formal charge, we write the number and then we write the charge. But for oxidation states, we write the charge and then the number above the element. And this is the other little thing for AP. Some oxidation numbers can be fractions. It depends on the particular element in question. That's not a very frequent thing, but they can be fractions. All right, so let's try some examples here real quick. So if I'm following my oxidation rules, assigning oxidation numbers, O in CO2 is going to get what? -2. Oxygen is always -2 unless it's in a peroxide or it's with fluorine. So based off of that, I know that this is going to be -4 then for the representation of the oxygen. This is a neutral compound, so they must add up to 0. So in that case, what does the carbon have to be to make it add up to 0? This has to be a +4. All right, so here, sulfur and fluorine. Actually, this is sulfur hexafluoride, but what do we assign the fluorine here? -1. And there's 6 of them, so that's -6, so that's a 0. So what must the sulfur, what's the oxidation state it must carry to make this work? This is +6. Good. Last but not least here on the nitrate. This case, it has to add up to -1 because the charge on the nitrate is -1. Okay, oxygen here, this is going to be -2, so that's -6. So what must the nitrogen be in this case? This one's +5. Very good. Simple way of assigning oxidation states.